These are your notes for Unit 4, Day 6 of Pre-Calculus. If you would like to see the warm-up, review question, or any homework questions we covered in class today, just look at the finished notes. So today we're going to talk about the conjugate pairs theorem and what a conjugate is, and then we're going to talk about the complex or imaginary zeros of polynomials. So the complex roots of a polynomial. So if we wanted to graph x squared plus 3, this would cross the it would cross the y-axis at 3. It's a happy parabola that moved 3 up, so it would look like this. And then remember, the roots are the x-intercepts. So notice on this graph, there are no x-intercepts. So it technically has no real roots. So it has no real roots. But remember how we can find x-intercepts? You set the y equal to 0 and solve. So if I take 0 is equal to x squared plus 3, and I solve this, you would subtract the 3 from both sides, and you get x squared equals negative 3. And then remember, to solve something that's squared, you would take the square root, put a plus or a minus in front. So x is going to equal plus or minus the square root of negative 3. Well, the square root of negative 3 doesn't exist. So remember, what we can do is we can pull out the imaginary number I, and so it'd be plus or minus I square root 3. And remember, I is the imaginary number, and it's equal to the square root of negative 1. And if you remember that I squared is equal to negative 1. So complex roots are your imaginary roots. So they're the roots that you would get when you set it equal to 0 and solve. You get imaginary numbers. You get the negative under the square root. And so in order to deal with them, you pull out an I, and then you leave the number in the square root alone. So it'll be plus or minus I square root 3 would be the complex roots of this polynomial. The conjugate pairs theorem, so remember, I don't know if you guys remember this or not, but conjugate would be if you had something like the square root of 4 plus 2, its conjugate would be the square root of 4 minus 2. You switch the sign in the middle. Or if you had 3 plus I, its conjugate would be 3 minus I. So it's the plus and the minus in the middle, so you change it. So those are conjugates. So 3 plus I and 3 minus I are conjugates. Or if I had 2 minus 5i, then 2 plus 5i would be its conjugate. What the conjugate pairs theorem says is if you know that x equals 3 plus I is a root of a solution, is a complex root, then its conjugate is also going to be a solution. Then x equals 3 minus I is also a root. They're both going to be solutions or roots to the equation. So in our example, it says a polynomial function of degree 5, so that means we're going to have an x to the 5th. It has real number zeros and complex zeros at 1, 5i, and 1 plus I. It wants you to find the remaining 2 zeros. So 1 0 is x equals 1, another 0 is x is equal to 5i, and a third 0 is 1 plus I. So those represent 3 zeros of my function. Since it's degree 5, then that means I should have a total of 5 solutions, or 5 zeros. Well, x equals 1 is a real solution, so that's the only guy that goes there. But x equals 5i is complex or imaginary, so that means its conjugate should also be a 0. The conjugate of positive 5i is negative 5i. So negative 5i and positive 5i will both be zeros or roots to this. And then again, 1 plus I is complex or imaginary. So its conjugate will also be a solution, which would be 1 minus I. So the two extra solutions are x equals negative 5i and x equals 1 minus I. So again, the conjugate pairs theorem says that if you know that a polynomial has an imaginary solution, then its conjugate would also be a solution. So just change the sign in front of the imaginary term. So writing the equation of a polynomial if you know its zeros. So find a polynomial of degree 4 whose coefficients are real numbers that have zeros at x equals 1, and x equals negative 4 plus I. Well, x equals 1 and x equals 1, we're good to go. X equals negative 4 plus I. If that's a solution, then its conjugate is also a solution. So that would be x equals negative 4 minus I. That would be the conjugate. Now remember, if we want to write the polynomial, we have to put these back in the parentheses. Well, x equals 1, its parentheses would be x minus 1. X equals 1, its parentheses would be x minus 1. x equals negative 4 plus I. We're going to add the 4 over and subtract the I over. And then that parentheses would be x plus 4 minus I. And this one we're going to add the 4 over and add the I over. And then that last parentheses would be x plus 4 plus I. And that would be my function. But notice typically in math, if our parentheses have i's in them, we have to multiply it out so it looks nicer. So we're going to multiply this out. So I'm going to multiply x minus 1 times x minus 1 first. X times x is x squared, and then I would have minus x, and plus 1. And on this one, if I multiply these guys together, I'm going to get x squared plus 4x plus xi, and then I'm going to get plus 4x plus 16 plus 4i, and then I'm going to get minus xi minus 4i and minus I squared. And then notice what cancels. I have a positive xi and a minus xi, those will cancel. And I have a positive 4i and a negative 4i, those will cancel. So now if I combine like terms, I get x squared minus 2x plus 1. And then in my other one, I get x squared plus 4x would be plus 8x. And then I have a positive 16. Do you remember what I squared is? Remember, I squared is negative 1. So the opposite of negative 1 would become plus 1. So my two parentheses could be x squared minus 2x plus 1 and x squared plus 8x plus 1. And if I wanted to go really far and get it all the way down, I could multiply these out. And I would get x to the 4th plus 8x cubed. And then plus x squared. And then minus 2x cubed minus 16x squared minus 2x. And then plus x squared plus 8x plus 1. And if I simplify all the way down, I get x to the 4th, 8x cubed minus 2x cubed would be 6x cubed. And then x squared minus 16x squared plus x squared would be negative 14x squared. And then negative 2x and positive 8x would be plus 6x and then plus 1. And that would be that polynomial who would have zeros at 1, 1, negative 4 plus I, and negative 4 minus I. All right, if we wanted to find all of the zeros of a polynomial function, we would have to find one zero first. And so remember from the rational root theorem, we could do all of the factors of negative 18, so plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 9, and plus or minus 18 over all of the factors of the leading coefficient, so plus or minus 1, plus or minus 3. I will not make you do that by hand, so let's go on Desmos and find all of our zeros. Desmos is only going to give us the real zeros. We'll still have to find the imaginary ones. So 3x to the 4th plus 5x to the 3rd plus 25x squared. Oops, I needed 25. 25x squared plus 45x, and then minus 18. And so the two real zeros that I get x equals negative 2, and then x equals 1/3. So those are going to be two real zeros, but notice it's a degree 4. So that means I also need two imaginary or complex zeros. So in order to find those, we're going to do some synthetic division. So if I put my solutions in the house, so I'm going to put negative 2 in the house, and then I get x to the 4th, x to the 3rd, x squared, x, and then my constant. So 3, 5, 25, 45, and negative 18. So I would bring down the first one, then 3, negative 6, negative 1, 2, 27, negative 54, negative 9, positive 18, 0. So that worked. So now if I write my depressed equation, I get 3x to the 3rd minus x squared plus 27x minus 9 equals 0. At this point, you try and see if you can factor this. If I factored by grouping, maybe it'll work. So on the first two, I can pull out a 3x squared, and I'm left with, oh, I can't pull out a 3x squared. I can just pull out an x squared, and I'm left with 3x minus 1. And on the next one, I can pull out a 27, and I'm left with 3x minus 3. So that didn't work, so I can't factor by grouping. But I do have another solution that works. I have 1/3 that works. So now if I take my depressed equation and do synthetic division with that, with 1/3, I'll get a new equation. So I'm going to do x to the third, x squared, 27, and my constant. And I get 3, -1, 27, and -9. Should be an x, not a 27. So now if I bring this down, 3 times the third is 1. Add going down, and that's 0. 0 times the third is 0. 27, +9, 0. So now my new solution, since that's an x to the third, this is an x squared, and x is my constant, I get x squared plus 27. And then if I set that equal to 0 and solve, that will give me my two other solutions. So subtract the 27, x equals -27. So x is going to equal plus or minus the square root of -27. So my two imaginary zeros are x is going to equal I plus or minus the square root of 27. And then if you simplified that, you would get x equals 3i, whoops, plus or minus, because 27 is 9 times 3, square root 9 times square root 3. So this is going to be x equals plus or minus 3i root 3. So either of those would be correct. So my four solutions, or all the zeros of this, would be x equals -2, x equals 1/3, and then x equals plus or minus, that should be plus or minus I, square root 27, or plus or minus 3i, square root 3. All right, gentlemen, so for our test, remember ways to study for it. You should review all your notes. You should review the finished notes. You should review any video notes that you need to. You should look over your homework and exit tickets. You should complete the book review homework. You should complete any Socratives that I have open to help you study, and the Socrative that we did in class probably today to help you review. Remember to study with a buddy, and to email me with any questions as you're studying, or you can come see me before or after school. So here is your homework. You have some homework questions on what we covered in class today, plus the review homework. So let me know